Hi all, this is Yuvraj Suresh Babu.
I'm Vikas Sunkara.
Today we'll be presenting the paper Optimal Mistake Bounds for Transductive Online Learning. At a high level, this paper asks a very natural question. If a learner is allowed to see all the future input examples in advance, but not their labels, does that help reduce the prediction mistakes? And if it does help, how much does it help? And that's the central problem studied in this work. So before going into the paper, let me first explain a very simple setting of this paper. In the online learning, the prediction happens one example at a time. So the learner does not get a fully labeled data set beforehand. Instead, examples arrive sequentially and the learner predicts and then the correct answer is revealed and this process repeats. And this paper ideally compares two versions of that process. And the first one is a standard online setting. Here, the learner only sees the current input and when the round begins, and it has no knowledge of the future input. The second one is the transductive online settings. Here, before the presentation even starts, prediction even starts, the learner is shown the entire sequence of the future input instances, but still does not know their labels. So the learner knows what examples are coming in, but not the correct answers. So the objective of the paper is to compare these two settings and answer one ideal question. If the learner knows the whole unlabeled input sequence in advance, how much can it reduce the number of mistakes? And now let's look at the standard online learning setup more concurrently. So there are two players, the adversary and the learner, and both know the hypothesis class H, which is basically the set of all possible labeling rules we are allowing. Then the interaction happens round by round. In each round, first the adversary chooses an input instance, which is called x of t, and then the learner predicts a label for that instance. After that, the adversary reveals the true label, and this continues one round at a time. And the important thing in the standard setting is that the learner does not know the future input in advance, as we saw earlier. The adversary's goal is to force as many mistakes as possible, while the learner's goal is to identify the correct rule and make as few mistakes as possible. And next is the transductive learning settings. And now let's compare that with this setting. So the overall game still involves the adversary and the learners and the prediction as usual. And in the very beginning, the adversary must reveal the entire sequence of input instances in advance. So the learner sees all the future inputs before making the first prediction. However, the learner still does not know the label. So the easiest way to remember is the future inputs are known here. And this is the exact advantage the learner gets in transcriptive settings. And that is a second effect. Oh, sorry. Yeah. And here the adversary actually gives the sequence initially itself, and the learner just keeps on predicting the correct label, and then the adversary reveals and tries to force a mistake here. And yeah, as far as the second effect, because the adversary had to commit the full sequence at the start, it can no longer keep changing the future inputs during this game. And so the compared to the standard setting, the learner becomes stronger and the adversary becomes weaker here.
All right. So now that we know in case of the transductive setting, the whole sequence is given in advance, is this knowledge of the sequence actually helpful? Well, for one, the adversary is at a disadvantage in this case, since in the standard online setting, the adversary can adaptively choose inputs to make learning the correct hypothesis very difficult for the learner. Since each of its inputs is going to be dependent on the answer it gives to the previous input. Naturally, in the transductive setting, since it commits to the entire sequence, it cannot adaptively choose inputs, so it has less opportunities to force a mistake. And similarly, learner is at an advantage because knowing the future on labeled data, it can force the adversary to either not force a mistake or confine it to a position where it's not able to force further mistakes than in case of the standard online setting. So essentially, for every hypothesis class H, the number of mistakes made in the transductive setting is always less than or equal to the number of mistakes made in the standard setting. So now this paper tries to look at how much this actually helps, and it tries to quantify that. All right, before we go into the proofs of the upper and lower bounds established, here are a few definitions that are helpful. So we know the hypothesis class is a subset of all possible binary functions that take in elements of our input space X as input and gives an output of either 0 or 1. We also have the little skull dimension for a given set, a hypothesis class, D, which basically means that there exists a shattered binary tree of depth D, where D is the maximum number of mistakes that the strongest adversary can make against an optimal learner. And we've also seen from our lectures that the optimal mistakes made in this case, given H and the input space, is D, since the shattered binary tree constructed acts as a kind of a guide for the adversary to force mistakes a certain way. Here's an example tree of depth 2, where each of these nodes, V1, V2, all the way to V7, represents some xj that belongs to the input space. In case of the standard online setting, these can be any values. The exact same tree is also used for the transductive setting, where V2 and V7 could possibly have the same input xj. So at each of these points, the output of the function that we're looking at is either 0 or 1. So for example, if you look at node V2, if the output is 0, the next node is V4. If the output is 1 at node V2, the next node is V5. And this binary function at each of these nodes basically gives us the direction in which our path goes. More on what a path means later on in the next slides. So now, for the case of this paper, the notations are as follows. The root node is represented using lambda, and all the children node are represented using some kind of substrings of a binary string. So if we look at this particular tree, we have 4 correct paths, that's 0, 0, 0, 1, 1, 0, and 1, 1. So we basically have 4 unique hypotheses in our hypothesis class. And for a depth of D, we would obviously have 2 to the D leaves, and our hypothesis class would have to have cardinality at least greater than or equal to 2 power D. So every leaf, again, is represented as a string B. We will have functions edge subscript B to indicate the paths. So for example, we've taken edge 0, 1 to be the true class in this example, which means at root node, the value of edge 0, 1 would be 0, which naturally means the next node is 0. And at that node, the root of the value of h of 0, 1 of 0 would be 1, which basically says from node 0, we go to node 0, 1. And on-path nodes are all nodes that lie in the path of HB. In this case, for H01, the on-path nodes are lambda, 0, and 0, 1. Off-path nodes are all other nodes. Typically, for minimum classes, off-path nodes are assigned value 0. And for probabilistic classes, which is the set of classes that this paper uses to establish the upper bound, the off-path nodes are assigned assigned value 1 with some small probability of the form 2 raised to some function of root of D. Again, there will be more on those in the later slides. Another thing that we're going to be looking at is something called the version space. So at each time instant t, version space h of t is basically all the hypotheses that belong to h, which are consistent with the labels up to point t. So which means whatever choice is made at x of t, your version space becomes smaller. But an adversary cannot always force a mistake. Say the given question or the given input to be asked is x of t. If all the h agree on that x of t, the learner obviously chooses that particular value which is common amongst all the values of h in the version space, and the adversary cannot force a mistake. On the other hand, let's say it can force a mistake. Let's say we choose 0 as the learner, but the adversary forces a mistake and says, no, the value of h of xt at that instant is supposed to be 1. This might not be a wise move for the adversary if by doing this, the version space reduces to a much smaller value. So the adversary always wants to make decisions based on whether in the future the learner would make more mistakes or not. And the learner obviously wants to reduce the version space to 1. So the main result that this paper tries to show is that the mistakes made in the transductive setting for a given class H with Littlestone dimension D grows tightly bound with some function of the form of square root of D. This obviously is a big jump, which basically tells us that in case of the transductive setting, knowing the future sequence allows for a lot fewer mistakes than in the case of standard online setting. All right, let's try to build some intuition on how this works. So based on how the paper has defined each node, 0, 1, 0, 1, 0, 1, 1, 1, and so on, each of these nodes are a reference to some value of x that's given in the input space. So 1, 0 could possibly be x5, 0, 1 could be x200, depending on the cardinality of the input space. So each of these basically point to a specific x that belongs to our input space. So let's say we're looking at path 101. We start at the root node. Let's say for some reason the learner chooses 0 to be the answer. The adversary can force the answer to be 1, and therefore there's a mistake that happens in the first level. Similarly, you can force mistakes at the next 2 levels in case of the standard online setting. So for this particular case, the number of mistakes would be 3. One made at lambda, one made at root 1, one made at node 1, 0. But if we commit to the sequence in advance, let's say the adversary tells the learner that it's going to be lambda, then 1, then 1, 0. Given this knowledge of the sequence, the learner can always choose to follow the direction in which the next question would be. So for example, as a learner, if I get lambda as the input, I would say the value of the function at lambda is 1, therefore coming to the next question. Now, if the adversary decides to force a mistake here, it would go to the other side of the branch. And naturally, everything on the right side of the branch, or the branch that follows all these red marked nodes, are the ones where the adversary has the highest opportunity to force mistakes. So by going to the other side of the branch, the adversary basically loses its ability to force the mistakes it would be able to force in case of the standard online settings. So that's just to build a little intuition about why it's better to know the sequence in advance. All right, let's look at the lower bound. The goal is to show that the learner makes a lower bound of root D mistakes. So the adversary's rule is as follows. At every round, it calculates the ratio to which at that particular round, h of xt is 1, where all the hypotheses until that point agree with the previous labels. And if this falls in a certain range, it would force a mistake. Otherwise, it would assign the majority label at that particular h of t. And this epsilon is chosen in the form as shown in the slide, and this is purely done to enforce the lower bound of root of d. So again, if h of t plus 1 over h of t is greater than or equal to epsilon, if a mistake is forced. Otherwise, it's 1 minus epsilon if a mistake is not forced. So knowing this, we can come up with the inequality shown on the screen. For a game that has n rounds and m mistakes, h of n plus 1 over cardinality of h can be expressed as follows. And we know that h has a Littlestone dimension of d, so it has to have at least 2 to the d cardinality. That gives us the second inequality. And we know for the game to end, our version space must eventually shrink to 1. Given all of these, we are able to establish our lower bound as shown on the screen, which is some function of the form root of d. And now, to calculate our upper bound, we must construct our hypothesis class such that its Littlestone dimension is d, but at the same time, it should be easy enough to be determined in a transductive setting. What does it mean for it to be easy enough to determine in a transductive setting? Take an example of the binary encoding of 11. It's 1, 0, 1, 1, where each of the bit could be either 0 or 1. So we would get a tree of depth d is equal to 4 in this case, since we have 4 different bits. And the adversary would essentially be able to force 4 different mistakes in case we expressed all the hypotheses in case of in the form of binary encodings where each bit can either be 0 or 1. But if you look at sparse encodings, it becomes a lot easier to predict the correct hypothesis without making too many mistakes. In this case, it would be easy to just predict 0. And whenever you eventually make a mistake, you know that bit is supposed to be 1 and you find the correct hypothesis class with just one mistake. That's kind of the idea, but the key is to note that we still ensure that the Littlestone dimension is D. So for a tree of depth D minus 1, we have the following notations where B is a substring of length D, where each bit is either 0 or 1. And we define the function of a specific string up to a point I to be the value of the next bit in that string. And the path is just the set of strings that start from the root node to the child node to the next child node and so on. So each child node has a value that is a string concatenation of the previous string that led the function to the next bit plus that particular bit. All right. So now we look at the construction of one particular hypothesis class. So if we look at a similar example as seen in the previous slides, we have a tree of depth 2. Since we have only 4 leaves, we have 4 unique hypotheses. That's defined as a function h00, h01, h10, and h11. If h01 is the correct hypothesis, lambda, 0, and 01 are on-path nodes and everything else is off-path. H of 01 gives the direction to go from the given node to the next node. So at lambda, it gives 0, at 0, it gives 1. And off-path nodes can either be assigned value 0 if they're minimal classes, or 1 if they're probabilistic classes with some small probability. It's always advantageous to have probabilistic classes since it's more likely for off-path nodes to be 0 for a large number of hypotheses. But if you have 1 or 1 or 2 hypothesis class with a value 1, you get to eliminate a lot more of the version space as you could in case of the minimal classes, which is why it's advantageous to have probabilistic classes. And now let's look at the learning strategy. Obviously, the naive learning strategy would be to keep guessing 0, since most of the values are going to be 0 if we have sparse encodings. So every time an adversary forces a mistake, our version space shrinks. In case of off-path nodes, guessing 0 is almost always correct, since we're looking at minimal classes or probabilistic classes. If adversary forces a mistake in this case, as in if it forces a mistake when we predict 0, but the actual value is 1, we have a huge shrinkage in the version space, since there's very few vectors or very few hypotheses that have value 1 in an off-path node. Similarly, on the on-path nodes, we need a real strategy. This naive strategy wouldn't work. But the problem is the adversary can give nodes in any order. So if it gives a lot of on-path nodes initially, it can force a lot more mistakes. So this requires some kind of fix, which is done through danger zone minimization. This will be explained in the next slide. And there's no way to know if a given node is on path or off path, which is also explained in the next slide through a strategy called splitting experts. And finally, only so many mistakes can be made before the strategy breaks, after which we have to move on to halving, which is also explained in the next slide. So our learning strategy is as follows. We choose a given range of a subset of our input sequence given by the of the adversary. And here Tmax is chosen as follows as given on the screen. So based on a given input, the prediction is decided by whether it reduces the space or the subset S by at least a factor of 1/3. So we choose the prediction B if SB is greater than or equal to 1/3 the cardinality of S. What does this mean? If neither S0 or S1 satisfy this, as in if you're given X is some node, S0 would be all of its children nodes that start with the bth child or the 0th child of the given xi. Similarly, S1 would be everything that's the one child of node xi. If the label is actually 1, xi could either be on or off path. We don't know this. So here, the strategy is for the learner to split into 2 experts and follow both these interpretations. And now eventually, the correct one would have only a lower bound of square root of d mistakes. Once all the labels are on for the danger zone sequence, we switch to halving, which is similar to SOA, except here we choose the B that maximizes the cardinality such that H of X is B. And similarly, with each of these cases, in case of danger zone minimization, the maximum mistakes is big O of log of T max, which is big O of root of D, which gives us the upper bound. The same upper bound is obtained with the splitting expert and also with the halving strategy. So that gives us the upper bound. So to conclude, we've proven both the lower bound and the upper bound, which gives us the tight bound on the mistakes made in the transductor setting. Now, though they've given, the paper has given an algorithm that can potentially find uh, an algorithm with only these tight bound mistakes with square root of D, it's computationally expensive since the sequence construction by the adversary is exponential and splitting experts by the learner is also exponential. And this result only holds true for a specifically engineered hypothesis class. It's not true for the general case. These are some of the major limitations of this paper. And with that, we come to the end of our presentation. Thank you.